So in this video, we're going to cover section 5.3, which is locating the real zeros of our polynomials. If in quadratics, we could almost factor all of our quadratics, but in these higher degree polynomials, there aren't so many direct ways to factor, and a little of it ends up being guess and check. But we have a handful of tools to help us figure out where our real zeros are. We've got the rational zero theorem, Descartes' rule of signs. We've got a bounds of real zeros and an intermediate value theorem. So the rational zero theorem tells us that if we've got this polynomial and it's got integer coefficients where the leading coefficient isn't zero, then any rational zero of f has to be of the form p over q, where p is a factor of the constant term and q is a factor of the leading coefficient, right? So this is really helpful for telling us what our rational zeros can be. Keep in mind that we could still have irrational zeros, or we could have imaginary zeros with imaginary numbers. So we'll start with this first example where we want to find the zeros of our function f of x is x to the third minus 5x squared plus 2x plus 8. First, you might look at this and say, oh, factor this by grouping. But when you think about it, I don't think you can factor it by grouping. It's not going to work. So let's use our rational zero theorem to see what the possible rational zeros are. And if we find one, we can just divide it out and then look at the remainder, which will be a quadratic. So since our leading coefficient is 1 and our constant term is 8, then we have all the factors of 8 divided by 1. So we've got plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. So that only gives us 8 rational zeros, and conveniently, they're all whole numbers. So we're going to use synthetic division to try to go really quickly through these 8 possibilities to see which of them are zeros, and then we can further factor the polynomial. So to do that, let's move to the whiteboard. All right, so I've set up our synthetic division for our first possible factor where k equals 1. Okay, so saying that the zero here is 1. And we're going to just go through our polynomial long division. So 1 times 1 is 1. We add these guys together, we get -4. 1 times -4 is -4. We add these together, we get -2. 1 times -2 is -2. We add them together, we get 6. So that tells us that 1 is not a root of this polynomial. So if we want to be systematic about this, we could try -1 next, or we can try 2. Let's try 2. So we have the same leading coefficients, 1, -5, 2, and 8. We're going to bring that 1 down. 2 times 1 is 2, which leaves us with -3. 2 times -3 is -6, which leaves us with -4. And 2 times -4 is -8, which leaves us with 0. Yes, this tells us that 2 is a possible zero. What that means is that our polynomial f of x can be factored as x minus 2, and we've got a 1 here, so we've got a 1x squared minus 3x minus 4. So these are just the coefficients coming from right here, and we know that this factor is x minus 2 because the root is a 2. Okay, so that's our first step to factoring this third degree polynomial. Basically, we use the rational zero theorem to get an idea of what some of the possible rational zeros could be. We tested a few of them out using synthetic division. And once we got one of them, we could factor that out. And now we just have to factor this remaining piece right here. And if you don't want to, we don't have to write that 0. So we've got x squared minus 3x minus 4. And we can see that this is going to factor to x minus 4 times x plus 1. So our f of x, oops. So I'm going to rewrite this as, oh, I'm in the, there we go. F of x is going to equal x minus 2 times x minus 4 times x plus 1. And there we go. We've completely factored our polynomial. So we can see the zeros are that x equals 2, x equals 4, and x equals -1. Okay. And it's true that all of these zeros happen to be a subset of the possible zeros that we had. Okay. So just to recap what we did, rational zero theorem, test some stuff out with synthetic division. Once we get one, once we're able to slightly factor this thing, usually the factoring gets easier and easier as you go. So you want to be careful about what the rational zero theorem doesn't do. It doesn't necessarily find any zeros for us. It just gives us a list of the possible zeros. It also doesn't tell us anything about the irrational zeros or the complex zeros. So if our polynomial only has irrational or complex zeros, give us any help. So we have some more tools. One is Descartes' rule of signs. If we have a polynomial coefficients, we're going to variation in sign, the change in sign of one coefficient to the next, either from positive to negative or vice versa. All right. So this is when it's written in descending order of degree. We're just going to look at the signs of the coefficients and see if they change or not, and count how many times they change. Descartes' rule of sign says that the number of positive real zeros is either the number of variations in sign of f of x, or it's going to be less than this by a multiple of 2. The number of negative real zeros is going to be the number of variations in sign of f of negative x, or less than this by an even number, or a multiple of 2. So let's take a look at this example. Here, our function changes sign 3 times. The first term to the second term is positive to negative. The second to the third is negative to positive, and the third to the fourth is positive to negative. So our function changes sign 3 times. So we have 3 or 1, because that's less than by 2, positive real zeros. Now, if we evaluate our function for f of negative x, notice when you plug in a negative x, it changes the sign of any term that has an odd degree exponent. Okay, so now when we look at this, we see that every term has a negative coefficient. So we don't change sign at all when the function is evaluated for negative x. What that means is that we have no negative real zeros. If we pair this with the rational zero test, we see that the only possible zeros are going to be positive 1, 2, and 4. Because remember, the rational zero test looks at the ratio of factors of our constant term 4 divided by factors of our leading term 1. Now the factors can be positive or negative, but by Descartes' rule, we know that there are no negative real zeros. So we really only have for our possible rational zeros 1, 2, and 4. So let's go ahead and check out how 1, 2, and 4 work. If any of these are some zeros, some rational zeros of our function. And we'll do that on the whiteboard. All right, so here's our function, and the zeros we want to test are 1, 2, and 4. So let's start with 1, and our coefficients are 1, -1, 4, and -4. I'm sorry, let me fix that. There we go. We'll drop that one to the bottom. And we will do the polynomial long division, or sorry, the synthetic division. And sure enough, x equals 1 is a factor. Okay, so this guy will factor to x minus 1 times, and remember, we're going to use these coefficients. This is going to be our squared term, our x term, and our constant term. X squared plus 4. All right. Now from here, we can see that the x squared plus 4 is going to factor into x can be +4 or x can be, or sorry, +2 or -2. Excuse me, x is not positive or -2. X is positive or -2i. Because if we take this x squared plus 4 and set it equal to 0 down here, and we try to solve for x, we see we end up taking the square root of a negative number. So x is plus or minus 2 times the square root of -1, which is 2i. So our polynomial factors to x minus 1 times x plus 2i times x minus 2i. And so the only real or even rational factor is this x minus 1. And then we have these two imaginary zeros. All right, so that's how we can completely factor this polynomial. I want you to notice that we are only going to cross the x-axis at x is -1. Maybe it's a good idea now to just take a quick minute and try to see what it looks like when we graph this guy. So we've got our end behavior. We're a third degree polynomial, and we've got a positive coefficient. So end behavior is going to look like that. The only time we cross the x-axis is at x is a +1. So we've got this guy. And then we can plug in our, let's say x is 0, and we're going to get a -9. So we know that our end behavior is down here. We cross our x-axis here, and we go positive here. But we don't really know anything else. We know we have these two imaginary roots, and they might make us do something weird, but they're not going to make us cross the x-axis again. Let's just take a really quick look at what this graph looks like on Desmos. Okay, so the graph of this function actually looks kind of similar to what we figured out just by factoring it to find any real zeros and looking at the ends behavior. So we have a couple techniques to find our zeros, our real zeros. If we have a polynomial with real coefficients and a positive leading coefficient, degree 1 or greater, and we call A some negative number and B a positive number, then we can say that B is the upper bound and A is the lower bound if the last row in synthetic division, when we divide by B, has no negative numbers, then B is an upper bound. If the last row in synthetic division, when we divide by A, has entries that alternate sign, then A is a lower bound. So again, if we divide by a number and the last row is all positives of synthetic division, then it's an upper bound. If we divide by a number and the last row alternates signs, then it is a lower bound to our real zeros. So let's take a second and try to figure out how this is going to work. If we want to identify the upper and lower bounds of the real zeros of this polynomial, we can division just by guessing and checking some different possible upper or lower bounds. So let's test some positive number as a potential upper bound. Let's test 2. Okay, it would be nice if there weren't any positive real zeros greater than 2. So we're going to divide this polynomial by x minus 2, and in synthetic division, that's just using a 2. We list the coefficients of our polynomial, and we drop that first coefficient to the bottom. 2 times 2 is 4. We add those together. 2 times 7 is 14. We add those together. 2 times 0 is 0, and we get a negative 21. So in this case, we actually are alternating sign here. So 2 is not necessarily an upper bound because the last row has a negative number, but there were also some positive numbers there. So let's try a higher number. Let's try a 3. We do the synthetic division on the 3. And you see we get all positive numbers in that final row. So according to the theorem, 3 is an upper bound because all the coefficients in the last row are non-negative. So this tells us that all, including the irrational zeros, are less than 3. Let's test for a lower bound. Let's try negative 3. We do the polynomial division. And we already see that we've got a 2 negatives in a row, so we are not alternating signs. So negative 3 is not a lower bound. So let's test an even lower number. Let's try negative 4. So far, we are alternating signs. We alternate signs all the time, so that tells us that negative 4 is a lower bound. So that tells us that all the real roots are going to be between negative 4 and 3. So if we want to use all of that together to find the real zeros of this function, we can look at the potential rational zeros. So we've got our factors of our coefficient. We've got our factors of our leading terms coefficient. We set those up as all the possible rationals, plus and minus here. So notice there's 8 numbers, but we can do positive or minus. So there's 16 possible rational zeros. But when we take a look at the upper and lower bounds, we get to eliminate anything that is greater than 3 or less than negative 4. And then that leaves us with just, how many is that? 9 different numbers. So that really narrowed it down a bit. And we can test these guys as if they are potential rational zeros using synthetic division. We'll start with our negative 3/2. We go through the synthetic division, and indeed, negative 3/2 is a rational zero. It's true, you might not have picked negative 3/2, which would leave you to do synthetic division on quite a few of these numbers, but it's a good thing synthetic division is fast. So you can see from that bottom row that the quotient is going to be 2x squared minus 14. So that's 2x squared minus 14 is the piece that we have to continue to factor. We can factor this using the square root method, and we get that x is plus or minus the square root of 7. So our roots are that negative 3/2, square root of 7, and negative square root of 7. Again, be careful using the upper and lower bounds theorem, because it's not really powerful enough to tell us a lot of stuff. We know that negative 4 is a lower bound, but it doesn't tell us that -3 would actually be a better lower bound, okay? The trade-off is that this theorem's pretty fast to use. I believe this is our last theorem in this section, and that's the intermediate value theorem. So here we have a polynomial with real coefficients, and we're going to say that a and b are some real numbers, where a is smaller than b. If our function evaluated at a and our function evaluated at b differ in sign, then there's at least one point, we'll call it C, that's between a and b, where our function is equal to 0. Basically, this theorem is saying is if at our function is negative and at another point our function is positive, that means we had to go through the x-axis. We had to change sign at some point, and at that point our function had to be equal to 0, right? To get from negative to positive or from positive to negative, we have to cross that x-axis, so our function has to go through 0. Again, the intermediate value theorem only tells us that there's a 0 somewhere. It can't prove that a 0 doesn't exist somewhere else, right? So we might have two functions that are, we might evaluate our function at 2 points and they're both positive. It doesn't mean our function didn't go below 0 and then back up. So to use our intermediate value theorem, we're going to pick some random points to evaluate our function at. And if one point's negative and another point's positive, we at least know that there's a root between those 2 points. So here's our function. We'll evaluate it at -1. We get a -1. We'll evaluate it at +1. We get a +1. So that means we have a root between -1 and +1. And in fact, when we graph this function, you see that it crosses the x-axis between -1 and +1. It doesn't tell us what that value is. It doesn't tell us how many times. I mean, we could have crossed the axis a bunch of times, but we knew that it crossed the axis there based on this intermediate value theorem.